Hello and welcome back to section 18. In this video we're going to look at how to work with complex numbers and complex exponentials. So if you recall in our previous videos we learned how to model a sinusoidal function or a cosine function using exponential functions so that they became easier to take derivatives of and integrate. Well, when we take the derivatives or integrals of those, we're going to get back complex numbers, basically a real part and an imaginary part. And then the goal is to be able to put everything back together and find the result. So there's a whole bunch of stuff here. So let's look at the visualizer to figure out what that is. So eventually we're going to be doing this, but before that, let's do some basic equation work. So if you consider, so let me redraw our diagram here. We have our real axis, which we consider in the x direction, our imaginary axis. So if this was back on one of the previous pages. And then we're going to have where we are currently, and we can model that a couple of different ways. So we already used Euler's to do that before. So in this direction, we'll have some x, and then we'll have some y. And so we can say that z is equal to x, so the x in the real direction, plus some y in the imaginary direction. I'll use the j again here. So we have some y component in the imaginary direction and some x component in the real direction. And that'll get us up here to this point, so we'll go over and then up. So we have z equal to x plus jy. That's our rectangular coordinate system. We can convert this into polar pretty easily. So this will be kind of a radius and an angle. So in this case, z, so this point z over here, we can still find that. In this case, it would be r, and then the angle theta. So here would be theta, and I would have my radius. And so we can find r by taking the magnitude of that. So r would be the square root of x squared plus y squared. And this should be a theta, not a 0. And theta would be our tangent inverse of opposite over adjacent, which in this case would be y over x. So same stuff that you've used before in trig. And then the ultimate goal is to get this all back into an exponential, because what happened is this, so kind of going all the way back, we had c plus or minus a, ce plus or minus at, and then out came a plus or minus a, and then ce plus or minus at. And this plus or minus a lot of times is going to pop out as some kind of a complex rectangular thing. And we want to turn it back into an exponential so we can do exponential math. So in exponent form, this will look like z is equal to r e to the j theta. And so we don't ever actually need to go to polar form, but it just kind of helps you to see how they relate. And then once we get all of that put back together, then we can do some math. So our math, just kind of a refresher, so say you had e to the 3t times e to the 2t. So once you kind of get everything up here, you have some kind of a j term up there. Well, then that becomes e to the 3 plus 2t, which is e to the 5t. So multiplying them means we add those two things up. If I have e to the 3t and then e to the, e divided by e to the 2t, well, that is the same thing as e to the 3t times e to the negative 2t. Remember, inverting will put us on the bottom. And then you should see where the pattern goes here. We get e to the 3 minus 2t, which is just e to the 1t. So just a refresher on exponential math. It's pretty nice. This is why we want to use it if we can. Alright, so let's head back to our example. So our example asks us to take the derivative of e to the 4t cosine of 3t. So you could do that using your standard integration rules, but you're going to end up getting a sine and a cosine function, and that's not really desirable. We'd like to keep it just as a cosine function if we could. Also, you may find that occasionally that will be harder to take the derivative or the integral of, especially if we get to the integral. So we already have this term as an exponential, so let's turn this one into an exponential. So I'm going to save the ddt for a little bit. E to the 4t, and this becomes the real part of e to the j 3t. So the neat thing about this real operator is I can move stuff around. So I'm going to move this e to the 4t inside so that we can better see what we're doing. So we're just going to move our real operator all the way outside here. So ddt, and I will have e to the 4t, e to the j3t, exponential math comes in here. So most of the time I'm going to drop this real operator and I'll bring it back later, but for this first example we won't. So we will get e to the 4 plus j3 quantity t. So now it's an exponential. I take the derivative of this. Our a here is 4 plus j3, so I will get the real operator. ddt gets replaced by 4 plus j3. E to the 4 plus j3 t. Then I want to turn this into an exponential, so I can add it back in here with this one. So we have now taken the derivative, and now we're just cleaning up this thing. So this is going to become, so if I draw this, I have 3 in the j, 4 in the y. This is a 3, 4, 5 triangle, and the angle is going to be this angle right here, and that is the tangent inverse of 3/4, which you will find to be 36.9 degrees. So that becomes 5e to the j 36.9 degrees. So this will be our phase shift. So we're actually going to get a phase shift out of this. And then we're going to multiply that all by e to the quantity 4 plus j3t. And we're almost there. So now all we do is notice that some of these terms both have a t. This term has a j, this term has a j. So we want to kind of rearrange our pieces so we can put together the things that have a j and the things that don't have a j. So we'll get the real operator, 5e to the, so let's break all these up. E to the j, 36.9 degrees, e to the 4t, and e to the j3t. So normally you wouldn't need to fully expand them, but it helps you see all our parts. So e to the 4t is the only one that doesn't have a j. So when I undo the real operator, it's the one that won't go back into a cosine. So we're going to pull that out along with this 5. So let's move that. So basically we have 5e to the 4t. Then we have the real operator acting on the remaining piece, which is e to the j. And then we have 3t plus 36.9 degrees. And then what happens? Well, we undo the real operator. And so this will become, so it's a real operator, which means we're going to get a cosine function. And then we just repeat this inside. So we get 5e to the 4t. This whole thing will become a cosine function. We just copy this piece down here, this 3t plus 36.9 degrees. So that'll be our answer. 5e raised to the 4t cosine 3t plus 36.9 degrees. Now, if you did the derivative without doing this, you're going to get something that looks like So again, you wouldn't want to do this because you're going to get a sine and a cosine. But if you did, you would get e to the 4t quantity cosine 3t and 4. That's a 4 cosine. 4 cosine 3t minus 3 sine 3t. So again, you wouldn't want to do it this way because you get a cosine and a sine function. Note that this and this are related through this identity. Cosine of u plus or minus v is equal to cosine u times cosine v minus plus, so flip the sign, whatever it is, sine u sine v. Sine u times sine v. So if you took this and applied this transformation, you would get this. Alright, and then you can always just check by plugging in some t's, so you can plug in t equals 0 and t equals 1, and you should see the same numbers pop out. But we prefer this form. We have a single cosine function. Alright, if you have any questions, feel free to reach out.